In this video, we are going to discuss some more advanced topics. Now, keep in mind, this is just a broad overview of the system. Everything we discuss in these videos, we are going to cover in much more depth later down the road. I just want to give a brief overview before we actually dive into the command line and start working with things. So if you don't understand things, don't worry. You can always go into Slack and ask me questions, and I'll be available and I'll try and answer your questions. But don't feel overwhelmed. Don't worry if you don't understand these topics. The first thing I want to cover is file descriptors. So file descriptors are non-negative integers the kernel uses to identify files accessed by a process. What does that mean? So non-negative integer, a non-negative number. So 1, 2, 3, 4, 5, for example. So when a process is created, it opens and reads and writes files. So for example, when I start Firefox and I'm using Firefox, Firefox has files that are open, it's reading and writing to the files. The kernel, when I start Firefox, returns a file descriptor that is used by Firefox to read or write to these files. Now when I start a shell, the shell opens 3 descriptors for every program it runs. It opens the standard input, that's input from the keyboard, standard output, which tends to go to the screen, and standard error. Now if these are not redirected, they all are connected to the terminal. So if I cat etc password, that is directed to the terminal. However, these can be redirected. These file descriptors can be redirected. Now recall, I said they're non-negative integers. So to redirect these, let's take the find command, for example. Now I'm not root, so I do not have access to the entire file system. If I do find /-name password, what that's essentially doing is searching for a file named password, file or directory, named password, starting in slash and going recursing down. So basically I'm saying search the whole file system, okay? Start with slash and go into the directories under slash and so on and so forth, and find everything named password. Now if I run this command, I get a bunch of output. I get a lot of permission denied because I'm not root. I don't have access to the entire file system. I also get this output, user bin password, so it actually found something. But this output is lost amongst all these errors, okay? So 3 file descriptors. The 2 we're going to cover right now. The other one is the input. We'll cover that later. We're not too concerned with that. But the 2 we're going to cover now is standard out and standard error. So when I run a program, 3 file descriptors are opened. Standard in, standard out, and standard error. Standard in, the file descriptor is 1, okay? And I can redirect this. So if I say 1 to a file, output.txt, standard error is still going to the screen. It's still connected to the terminal here. So I'm getting all the errors. But if I display the output of output.txt, if I display the contents of output.txt, I see I redirected standard out file descriptor 1 to this file. So this is the output from the command. Now I can also redirect standard error. So if I do the same command, this time to errors.txt. So I'm redirecting with this little greater than symbol, and I'm redirecting the file descriptor 2 to the file errors.txt. Now I see standard out. I didn't redirect it, so it's still connected to the terminal. So I see the output from standard out. And if I display the content of errors.txt, I see all the errors. So those are the standard out and standard error file descriptors. I've discussed processes a lot. I've talked a lot about processes. So when I start Firefox, there's a process, a Firefox process. So from the user's point of view, a process is an instance of a running program. When we execute a program, the kernel allocates resources for the program. and sets up data structures used to track information about the process. From the kernel's view, processes are something that it must share finite resources such as memory, CPU time, network bandwidth, and so on for. There is something called fork, and that means that processes can create new processes using the fork system call, okay? So if I start a process, it can actually fork and create new processes. The process that calls fork is called the parent process. And all processes started by the parent process by way of fork are known as child processes. And these child processes can also start processes of their own, and these are descendants of the parents. So, for example, when you start the shell and type a command, the shell process forks a new process for the command, and the commands process is a child of the parent, the shell. So let's do this. If I type in bash, okay, and I go to another terminal and I log in as another user, or another login, and I do ps-au Daniel, I see there are 3 instances of bash. One of them is my login shell, the other is the bash I typed in over in the other terminal, and the bash login shell that I'm in currently. So 3 instances of bash. Now, if I want to look at the parent process for these bash processes here, I can do pstree -s-p and then this number here. This number is called the process ID identifier. The PID, the process identifier. It identifies, it's the numeric identifier for a process running on the system. Every process has its own identifier. It also has a parent identifier, a parent process identifier. So if I do pstree -s-p 22369, I see systemd login bash pstree. Now notice pstree was forked from bash, from my shell. This is the parent process, this is the child process. This is the parent process of this, and this is the parent process of everything. If I do pstree -s-p 22352, I see essentially the same thing, but I see that this time bash is the parent process of bash, right? And coming back over into this terminal, coming back over into this terminal, we know that we were in bash and we typed bash, right? So the parent process is the bash that we were already in. When we typed bash, we started a new program, bash, and that is the child process. So the parent of this bash session is actually bash. That's kind of hard to explain, but essentially that is forking. Now, what is a good way to demonstrate forking? Every process has an environment, which is just a list of key value pairs that determine how the process behaves. So when a new process is created with fork, the environment of the parent process is inherited. So, type in exit again, type in env, and I can see these key value pairs. This is my environment, okay? And I can create one of these environment variables, I'll call it testing, equals, and give it some value, foo, okay? Now, if I echo testing, I created this environment variable testing, okay? And it has a value of foo. So when I type in bash, which forks a new bash process, and I echo testing, there it is, the value of foo. The value is foo. Now if I come over to this other terminal over here, okay, let's just say I exit, and I log in, and I echo testing, nothing set, no value, okay? Now, if I exit again and I create a new one, let's say export test2 equals bar, and I echo test2, I see that it has a value of bar, start a new bash process, whose parent process is bash, and I echo test2, we see that the child process inherited this environment variable from the parent process. Come over here, echo test2, and we see that it's not there. Okay, that's because this process does not have the same parent process as this process. Okay, final thing I want to discuss, actually one more topic after this, but another thing I want to discuss with regards to processes is every process has limits on the amount of resources that it can use. Each limit has two associated values. It has a soft limit. The soft limit limits the amount of resources the process can use, and there's a hard limit. The hard limit is the ceiling on which the soft limit can be set. Okay? So a process can change its soft limit, but it cannot go any higher than what the hard limit is. So, for example, any user on the system can only have a finite amount of open file descriptors, okay, at any given time. To see how many file descriptors a user can have, we type in ulimit-n, and that says 1024. So at any given time, I can have 1024 open file descriptors. Now, if that's the soft limit, and let's say the hard limit is 2048, I can adjust the soft limit, I can change the value using ulimit as well to 2048, but I cannot go any higher than the hard limit. So we use ulimit to get and set these values. Ulimit seems like a command, it's actually a bash built-in, and we'll discuss the difference between commands and bash built-ins in a different lesson. The last thing as far as processes go is that in order to see my processes, and we'll discuss the output of this in further detail, in order to see my own process, ps-au Daniel, these are my processes. More detailed output, ps-aux, and we can see all the processes running on the system. Notice there are two bashes here. One has a dash in front of it, one does not. The one with the dash in front of it is my login shell. It is the shell that is executed when I log into the system. The second one is when I typed in bash, that is the shell that I executed. So the first one, bash, if it has a dash in front of it, it's known as your login shell. We'll get into the differences between the different shell types later. Finally, the last thing I want to discuss in the more advanced topic is signals. Signals are used to inform a process of an event or a condition that has occurred. So the kill command, for example, is used to send a signal to a process. So if I type in kill, and then the process identifier, which is right here, 22444, that'll kill that bash process. Okay? Now, the kill command is used to send the signal sigint, and sigint tells the process die. Okay? It kills the process. There are other commands, other signals, so I'm just going to cover two right now. So cat, if I type in cat and I hit Control-C, this sends a sigint to the process and says it kills the process. Okay, memorize that. Control-C kills the process. Now, if I type in cat and then I type in Control-Z, that sends a sig stop, the signal stop, to the process, essentially suspending the process. And if I type in FG, that means foreground, that brings it back to the foreground. Control-Z, suspend it, foreground, bring it back. Okay? Now, if I do a ps-aux and I grep for cat, I see that cat, the first one here has a PID of 22466. So if I kill it, that sends a SIGINT to the process, and I now see that it's terminated. So those are signals. That concludes the lessons for this week. Next week we will actually get into building our own Linux from scratch. And I look forward to seeing you then, or talking to you then.